Dear students, we begin this lecture by defining homeomorphism between two metric spaces. Let X and Y be metric spaces. Let X and Y be metric spaces a function f from a function f from a function f from x to y is called homeomorphism. It's called homeomorphism if first f from x to y is 1 1, second statement f is on 2, third f is continuous, f is continuous, and f inverse is also continuous. Note that f inverse is defined because f is 1 1 and on 2. It is bijective function, and f inverse, which is function from y to x, is continuous. If such a function exists, then x and y are said to be homeomorphic. If such a function f exists, such a function f from x to y exists, such a function means satisfying all these properties, then f and y, then x and y are said to be homeomorphic. Said to be homeomorphic. Next definition which we will see is graph of f. A function f from x to y we consider a function f from x to y where we may assume that x and y are metric spaces. It is not necessary to have metric spaces, but let me assume that x and y are metric spaces. It is not necessary for defining graph where x and y are sets, you can say, so, or metric spaces. We are dealing with metric spaces only. In fact, we are dealing with non-linear spaces which are complete, where x and y are sets. Graph of f is defined as the graph of f is defined as collection of all pre-images and images. So it is xtx, where x belongs to x and I should write fx, and fx obviously belongs to y. So it is collection of all pre-images and images, all order pairs where first coordinate is pre-image and second coordinate is image. Geometrically, you can visualize, if we consider a real valued function of real variable. So what I mean by real valued function of real variable, I mean a function f from x to y where both x and y are subsets of R, that is pre-images and images are real numbers. Then we can visualize graph of f in this fashion. It consists of all order pairs. Okay, so I could take the point here, and it consists of all order pairs x and y, where y is actually equals to fx. So it consists of all order pairs, and if we collect all such a order pairs, or in this case all such a points, then we will obtain the graph of f. So this curve we can call it as graph of f for real valued functions of real variables. Now we want to establish closed graph theorem. So in order to prove closed graph theorem, we will need definition of graph of function, which we have seen, and definition of homeomorphism is needed for some few other results. So one of the important results in functional analysis is closed graph theorem. Closed graph theorem. The statement is, let T be let B and B dash, let B and B dash be Banach spaces. Let B and B dash be Banach spaces. A linear transformation T from B to B dash is continuous if and only if graph of T is closed subset, or you may say closed linear subspace, is closed subset of product matrix space B cross B dash. So linear transformation from one Banach space from one Banach space to another Banach space is continuous if and only if graph of T is closed subset of B cross B dash. So it is two-way implication, the closed graph theorem, and proof will be in two parts. We will assume that T is continuous and we will prove that graph of T is closed, and conversely we will assume that graph of T is closed subset of B cross B dash and we will prove that T is continuous. So we will see the proof in next lecture. Thank you.